So for today's tutorial, I think it will be ideal if you download both of these files and they are already ready to run. You can run them locally or on Google Colab or something. I think it's up to you. I think, of course, if you can run it in your machine and just make sure it works, it's probably fine. Especially if you can run it from the command line, like not using like Google, like these like Jupyter notebooks or Colab style notebooks. Um, because one of the reasons why I specifically wrote this one, like run functional Py, is to support like command line arguments. And this is something that I use extensively in my experiments. Command line arguments are very convenient, and I will go over them later. But yeah, the idea is that you should be running this from like a command line interface. So yeah, just if you haven't like set up your environment, I mean, I would suggest you download something like Mini Conda. Um, if you haven't like done that, like you download it for like Miniconda for Windows or for like Linux or for Mac OS or whatever OS you have. You set it up, then you will probably like create like an environment, and the command to create an environment is something like conda create. Maybe I can just make like a notepad. Yeah, something like conda create name of environment or something, I think. Um, and then no, it's like conda create uh, like name. Okay, and then the environment name. Um, and then you would install like you would like activate this environment, and then you would like install like things like Pytorch. Pytorch is probably like the most important thing that you need to install for now. I'm using like Pytorch like 1 point something. Right now there's a Pytorch 2.0. Um, but it has a few differences. I think you can install. I think this tutorial should be compatible with both. But for now, I guess like you need like newer versions of everything if you're using the new PyTorch. Otherwise, you can just use like the other one. And if you use like something like Conda usually would take charge of installing all the dependencies. So I would suggest using Conda when you're like working on with these kind of like scientific packages. Yeah, it would like probably if you wouldn't have installed that, it would take a while. But then after that, it should like basically install everything. And then sometimes when you're like working with a new repository, sometimes like you would like maybe if it's like a local repository, you would like do something like pip install -e like, and this means that it's installing like locally from the direct the current working address that you are working with. Um, so let's say that we are inside of a GitHub repository called uh, like diffusers, like the one um, from like coding phase, and you want to install it from source, from like locally, you would install it like something like this. Of course, there's other ways to install like Python packages, like directly install it from their package manager, the pip, and that's another way. So usually when you install it like either of these ways, sometimes they already have like some requirements, like in terms of other dependencies that you may need to install that are usually saved in a requirement.txt file. Um, in this case, for this tutorial, I didn't make any requirements, but I can tell you that at least aside from like PyTorch, which is probably something that yeah, you would need for any kind of experiment in this area. I think the only other package that I use that is not part of like this, like that is not going to be installed with this, it's called AINOps. And AINOps is a package for scientific manipulation of arrays and matrices and tensors. So you can install that like quickly, just pip install AINOps. And I will show you later also like why NOps is like very useful with like some practical examples of things that we would do in Pytorch and like NumPy and how like NOps basically what it doesn't really like simplify it, but it makes it much more readable. And I think being readable it's very important for code because when you want to make changes or when you want to work with someone else, it's much easier if you know the code that you have it has comments. It's like written in a way that is clear because it's much easier to like get people on board on whatever you're working with. Of course, well, it cannot sometimes like cannot be perfect, like making like perfectly readable code or perfectly I don't know modular code can be like not so easy. But I would still say that that's like kind of like some trade-off that we need to like when doing like software engineering in general. Um, and I would say that yeah, software engineering is indeed very important for this kind of deep learning stuff. As I mentioned, deep learning doesn't have like a theory. Yeah, there's some theories that people try to make about why do something in deep learning works, but in reality, deep learning is empirical based and it's based on experimental results, and therefore, like making good experiments, it's at its core of at the core of deep learning. So um, that's why I think like the coding part, not only like the aspect, it's like the coding itself, like the style and kind of like how to write, my opinion, clean code is very important. So did all of you already set up your kind of your environment or something? Mm, well, anyway, um, I would like kind of like start. If you have like any questions at any point, like oh like code is too small or anything, just let me know. But say something because otherwise I don't know. So can you see my code now?
Yes.
Yes.
Okay. So this is like the from the Blitz tutorial that I mentioned. If you like Google it up like Pytorch deep learning Blitz tutorial or something, it's the first thing that should appear in Google. So there's nothing in there that I changed. Basically, the objective of this tutorial is to like code all of the components of simple CNN for image recognition on Cypher. And it includes basically, as I mentioned, yeah, all of the like simple components, like the minimal components that you would need to do that. And so the first thing that we would do, usually we would like import all of the packages that we would need. In this case, because I just copied it from the tutorial, I just copied in the same number of blocks that they have, but ideally, and therefore you have some imports in the middle of the file. But in like I would say like in a real or like a more readable code, usually you would have all of your imports at the start of the file. So first like import everything. I will show you like the difference later. That's like kind of like the recommendation, like keeping all of your import at the beginning. In this case, mostly like we're using like Torch and Torch Vision um, to like kind of like do most of the things that we need. And then the thing that they start with first in this tutorial is kind of like the data processing. And in general, data processing is one of the pre-processing and processing are probably some of the most important things that you can do. Later on, when I show you like my other version of this file, you would see that actually my data processing part is actually takes, I would say, probably the most number of lines in the code. And I would say that that's a good baseline for anything that you do because honestly, uh, like data is at the core of deep learning. Like if you have good data, like good pre-processing strategies, good augmentations, these kind of things can go a very long way when doing anything related to like deep learning or yeah. So that's why data pre-processing is very important. In this case, like we keep it very simple. We just make a simple transform, which is going to take an image and it's going to make it into a Pytorch tensor so that we can then do all of these like fancy operations like auto differentiation and other things like GPU implementation by making use of like Pytorch. Then after that, because neural networks expect data to be in a certain range. In particular, like a normalized range, we would like then normalize the images so that assuming that the mean per each channel and the standard deviation per each channel is 0.5. And what we would like to do is basically have the image having an average of 0 and kind of like being between the range of -1 to 1. That way, like activation functions and other like functions like kind of are like within a certain range. It's also easier for uh, making computations of the gradients and other things. Then aside from that, when we are like training something, we would always like design like a batch size that is closely related to, okay, like the number of images that we are going to have in each iteration. And after that, usually this is like, again, very closely related to two things. One of the things that batch size is related is, of course, the number of images per iteration, but at the same time, it's also related to the computational cost in terms of like VRAM that we are going to use and also like the GPU utilization. So basically, if we increase the like batch size, usually we would be able to move more images to the GPU, and GPUs make better use of like uh, of parallelization. So basically, when we process like multiple images at the same time, it's going to be more efficient than uh, processing multiple images is more efficient or faster than processing images sequentially. So for example, if we process like one by one, it's going to be very slow compared to if, let's say, we process like, I don't know, 16 by 16. I mean like 16 images like side by side. And that's why in deep learning, we have, or well, not in deep learning, but when we're talking with GPUs, we have two terms that I think you should get very familiar with because you will be using them a lot: throughput and latency. So these two terms are closely related. And the first one, when we mean it's like latency, we mean like, okay, like how many seconds does it take to process an image in this case? So let's say that it takes us like 1 second per image. The throughput at the same time, it's like how many images can we process in a second? And you will be thinking that these two things should be like the inverse. Um, like for example, if this is like, let's say like it takes, let's say 2 seconds per image. So we will be thinking that it will be taking us we could process 0.5 images per second, or that's what we assume. But the thing is that in general, like this throughput and latency are directly related to the like GPU or any accelerator that you're using, like CPU or GPU or TPU or any other accelerator is going to have like different relations of this throughput and latency. Sometimes when you, let's say you process like one image like in without a batch, like using batch size one, the latency can be like a certain number, but when you increase like the throughput, like by increasing the number of images per batch, then actually the throughput can be like much higher than this theoretical value. So that's why like batch size is very important. At the same time, batch size also so that's like about the GPU or accelerator utilization. The second one is about the VRAM. So when we increase that, we are basically moving more data to the GPU, and therefore the GPU has like its own internal memory, like the video random access memory in this case. And usually it will have like its limitations. Like for example, consumer cards right now have like what 6, 8 gigabytes. Newer ones have like 10, 11, 12. Like the state of the art, like for consumer, like the 4090 and the 3090 both have 24 gigabytes, if I remember correctly. And then like industrial level GPUs would have much more like VRAM. Like for example, like an A100 GPU would have 40 or 80 gigabytes. An H100, which is like the state of the art, like current state of the art for like NVIDIA GPUs, has I think even more, like 100 gigabytes of VRAM. This is not only useful because you can increase the batch size, but in general, like if you have a very large model, you can train it on a single GPU. So that's how the batch size. So as I mentioned, yeah, basically we already make our transform. We like have our batch size, and therefore like now we want to load our data sets. For now, we'll be using like simple like Torch Vision data sets. They already include a lot of data sets like Cypher and MNIST. And right now, as far as I know, they are increasing, like they are also like adding even like some fine-grained data sets. But for now, we'll be using like Cypher. And usually like these Torch Vision data sets, they follow a similar structure of what do they expect when you are using this function, this class. They will be expecting like some like root directory where do you store your data. In this case, let's say we store it in data, or we can also store it like anywhere we want. We can store it in the same directory if we want. For now, let's say it's in data. And then it will have like some parameter to choose like which split of the data set do you want, like either like the training set or the testing set. Then in case you don't have the data set already, it sometimes would have an option to download the data set. In this case, they have this option. So it will, if you have like false, it would expect you to have already downloaded. But in this case, we use true, and it will download it automatically. And finally, it would include this transform, because it will like basically take each image and apply this transformation that we described here. So we are going to convert each image from like either a NumPy array or any other like structure that they have, uh, and then they will make it into like a Pytorch tensor, and then we will like normalize it. Later on, I will show you more transforms, and later on we will also go to the structure of how is this like dataset class in the Torch Vision usually structure. You will see what it's actually doing like behind the line, behind the I don't know, behind the something. Anyway, yeah, so for the train loader, this is another class provided by Torch, and what it takes is one of these Torch Vision dataset classes, and it will like make an iterable like function out of it. So in this case, uh, like what we want is to make like take this data set and return it in a way that we can like process it in a batch. So it will like basically do a lot of like optimization in the background, and it will like use like different CPU threads to like basically process like these images in parallel, and then it will return um, something like at each iteration, something like batch size, number of channels, image width, and image height, a tensor in this shape, which is compatible with like most common deep learning pipelines. And the batch size, again, it's something that we decided beforehand, so we should set it here. Number of workers is related to the like CPU processing. This is done in parallel. So how many like actually this is like number of threads. So like how many threads do we want to like use this like want to like be working on this on the pre-processing. And then shuffle means that we want to shuffle like the data set. Originally data set it's, let's say, order 1 2 3 4 5. Well, and let's say 1 2 3 4 5 are all from the same class. When we shuffle, it will take like basically any like random like number in the data set. So maybe it will take like 1 to 1 then, but then the next one, instead of being like 2, it will be maybe like 10 or any other value in the data set. And the way that we do it this way is because we use a stochastic gradient descent for training these networks. So it's what an stochastic process means. It's random. Like at each iteration, we take different values. And it has been said that this randomness actually helps like these neural networks with generalization, because at each step they would like be optimizing for different kinds of inputs. So this randomness can be sometimes helpful. So we do that for the training dataset, and we also do it for the testing dataset. So After that, this is just mostly for visualization. In a lot of cases, we wouldn't be doing that. But yeah, like basically one thing that we can do is we define the name of our classes so that later on when we are like doing some debugging of does this work or not, or what are the predictions that our model make, we can, okay, look at the prediction and see if they are correct or not. Again, I suggest that when you're writing a function in the future, like always do your imports at the beginning. But again, I copied it from their tutorial, so just to like keep it the same. Then after this is a function for visualization. They take an image like a Pytorch tensor, and then they do unnormalization. So remember that we normalize it. So now we unnormalize it, and we make it into a NumPy array, so that then we can visualize it using like an image visualization library. Like, well, this is like for figures, like PLT, to visualize the image. And then I think if you like, for example, like for now we are not going to like be like visualizing the images, but if you want to visualize the images, like you can use like this function here, image show. And to like do that, first we would like take this train loader, and as I mentioned, it's an iterable uh, function. Like it's an iterable structure. So if we use this iter yeah, like function in Python, and this like next function, basically what it will return is the next the first item in this iterable function. So in this case, this is the equivalent of when you're in the training loop, the first pair of images and labels. And again, we can like visualize that if we want to see like process our data. Usually this is something that we would do outside of the training. If you want to do like any kind of pre-processing, like Jupyter notebooks are very good for this. Of course, you can also like use traditional Python files to do this pre-processing. And the idea is that we want to visualize the data that we are working with. We want to make sure that whatever pre-processing or like that we are doing, any transformations, like they make sense. And the results that we are getting from this like visualization is indeed all, yeah, it all makes sense. Now, okay, so far we have covered like the data pre-processing and data processing aspect. Now after that, we are going to be moving to the okay, like the neural network model part, and then finally after that the training. But for now, until here, like with the data processing, any questions? If not, or if you have, just ask. If you have questions at any point, please just ask. Don't be shy and just ask. Like you can interrupt me. Otherwise, I will just continue. So for the neural network part, we are going to be like all of usually you don't need to like structure it this way, but I would say this is the preferred way to structure neural networks when using Pytorch. It's basically using classes. Um, so I guess you know what's a class, but if you don't, well, I do not know. No, just kidding. No, it's just like something like basically like an abstraction. You're like using software engineering in this case to like kind of define like an instance of some particular kind of category. In this case, it's like this category like neural network model, which has it's taking in like some functions that they define. In particular, there's these two that they always define, like the init and the forward. In the init, we would like, okay, like all like classes use this. So this is like standard. We will be taking in like basically defining like the design of our network. In this case, like how many layers, like, okay, the size of the layers and all of that. And then in the forward function, we would just be implementing like what's known as like the forward or yeah, like the forward pass of the neural network. So in this case, it's like a very like simple CNN that is similar to the net, which is a net from like 1989 made by Jan LeCun. And it basically takes in like the first, this is like a convolutional 2D layer, has like an input of, this is like number of input channels, a number of input channels, uh, number of output channels, and like the kernel size of the convolution. So this is like 3 input channels. We get 6 output channels, and it has a kernel size of 5. Then after that, we apply a match pooling layer. Again, for the match pooling layer, if I remember correctly, the first parameter is like the stride, and then the second one is the, no, the first one is the kernel size, and then the second one is the stride, or it was the other way around. Uh, I forgot. Anyway, it's one is like the kernel size, and the other one is the stride. Later on, I will like talk a little bit more about like kind of how does this change the dimensions of like the neural network. But for now, what you need to know is that this is like a very simple convolution architecture, like just convolutions followed by pooling layers, and then some activation function. Like the activation function applies nonlinearity, so that this becomes a nonlinear, like neural networks become nonlinear functions. And therefore that's why they can model in paper any kind of function. If we wouldn't include this nonlinearity, this will be a combination of linear functions, and therefore the amount of functions that you can describe is very limited. And then finally, after we do all of the convolutions, what we'll be doing is, because this is like a sequence of batch size, number of channels, and certain like height and width. What we'll be doing is we do like flattening. They use this torch flattening function, which what it does, it's convert this from like like this tensor with 4 dimensions. It convert it into like a tensor with uh, like one single dimension, like 2 dimensions. That actually it will be basically like the multiplication of this number of channels times the height times the width. So now you go from 4 dimensions to 2 dimensions by flattening these 3 dimensions here in the back. And the way that we do that is because now we are going to like basically combine all of these features like into like one single linear layer. And then we are going to like apply this yeah, like linear layer here, like a fully connected layer. And that's what we do here. We apply another nonlinearity, and then we do that like basically 3 times before making our final prediction that is supposed to be, in this case, because we're working with Cypher 10, we have 10 classes, so we are ending up with like 10 classes at the end. Again, I mentioned that we use this NN model, and I didn't mention that much why, except from, okay, it's a class that we are kind of inheriting from this class. One of the important things that all of these class have is that the original NN model, it's supporting like this auto differentiation or autograd kind of like functionality, which is like at the core of like a tensor, like this deep learning library, like either Pytorch or TensorFlow. They all support this autograd functionality to allow us to compute backpropagation, to compute gradients through these functions uh, effortlessly. Because otherwise, if you ever take a deep learning class or a machine learning class, sometimes they would like tell us to do the backpropagation by hand, or well, by code. And in that case, for example, like we know like we have like an activation function like the sigmoid, which is 1e minus x. In this case, this is like the function if we want to like do the backpropagation. I forgot like what's the like derivative for this function. I think it was like x times e minus x or something, or something like that. Yeah, I think it was something like that. Anyway, this kind of, so in the, like if you would do that like without this autograd functionality, basically you would have to be computing this derivative yourself, and then aside from like computing like a forward function, you would also have to define a backward function that computes these derivatives for each of these layers one by one in order to get the gradients that you need to yeah, basically optimize your network. And you may need to do that if you do like a deep learning course, and I tell you it's not fun. So that's what the, in simple ways, that's what we can assume, that the NN model and the Pytorch sensors, like they support this functionality by this autograd functionality. So yeah, and then after that, because we want to make sure that we make use of any accelerator, if we have, let's say, like a GPU or something, we usually code something like this, like basically like a torch device. If like we have like CUDA available, we are going to be moving our net. We are first going to be instantiating an instance of our network using this syntax, and then we will be moving our network to uh, like our device, either like if it's like on GPU, it's on GPU, and if it's on CPU, it stays on CPU. After that, as I have been talking a lot about like the gradients and stuff, so like again, deep learning is basically just like what they have in common with machine learning is that all of these disciplines, they are based on, okay, given a cost function, like a loss function, we want to optimize automatically a network or like some parameters based on some on the loss function using backpropagation. And then to do that, we need like an optimizer to handle this process of updating the network. And if again, if you take like a deep learning class, like an optimizer, what it's doing, I think under the background, it's that we have like some gradient for like these cost functions that we compute. So we have first this cost function. This cost function in this case is the cross entropy loss. And what it's doing is basically, in simple terms, computing the difference between the ground truth label and the prediction that we make. So let's say that the ground truth originally it was supposed to be like car ID 0, and we made like a prediction that no, it's a plane ID 1, and therefore it's going to like compute the difference between this and use this as the guide for the optimizer. In reality, this is like actually not computed using these uh, discrete variables, and it actually, for example, like you would have like an actual probability. It's more like, instead of being like plain 0.1, it's actually like a vector of probabilities. Let's say like 0.1, 0.3, 0.6 or something, and therefore like the correct probability should be something like 1, 0, and 0, and therefore it's going to be computing like the difference between this and this and this and this and this, and that's what it does. That's what, in simple terms, what it does. Of course there's other losses, but I think that should give you like a rough idea. Basically computing the differences between like the ground truth predictions and the ground truth and the predictions. Then after that, we know, okay, like it has like some cost. Like in this case, the cost is that originally it should have been predicting like car and it only predicted plane. So actually the difference is something like 0.9 plus 0.3 plus 0.6, and we do like some average of that. It's not really like that, but let's say that we have like something like, okay, like our loss function is actually like 0.5. So we know that it's 0.5, and because we know that we have this computation, basically we can compute the derivative behind each of these functions, and we are going to get a values to update all of these parameters. And what the optimizer does, it's kind of like taking care of this like changing in the parameters. So we go from like originally, let's say that the parameter are p in the like previous step t minus 1, and therefore what we want the optimizer to do is to optimize these parameters to be now obtain the state at pt, and the state at pt actually is, well, like for something like simple like sgd, it's actually to the state at t minus 1 plus like it's something related to like the gradient times maybe like some like other like kind of like weight or something. But basically, as you can imagine, we have the original value of the gradient, and we are adding some value based on like how wrong the prediction is. That's kind of the idea that we are using. And in general, like yeah, these are gradients, so these things have like kind of direction. Uh, and if we assume that this is like a, let's say like something like a 2D field, um, 2D optimization landscape, it will be something like this that we see on the right, or maybe like something like this. Originally, we start from these red points here in the like here like some points like that it's like the loss is very high, and based on these loss functions, so this is the value of the loss function, the color in this map, and then based on that, we will like basically we be computing like um, the the derivatives, and this derivative basically will be telling us, okay, like the loss is like higher in this particular direction or something. And the optimizer, what it does is it just move the parameters. In this case, we only have like I think like two parameters, like x and y. So they usually use something simple like to visualize these kind of ideas using something like linear regression, but the same kind of ideas apply to all kinds of machine learning problems. And therefore, what we want the optimizer to do is to basically like point in the right direction of, okay, where should we move so that we get to this lowest point in this kind of figure. Yeah, so basically it wants us to tell us that, okay, we move here and then we move here and then we move here until we get to this point, like this passing, like the blue point in the middle where the loss is supposed to be at its lowest point. So that's what the optimization is kind of doing, like the optimizer is kind of doing. And in particular, like you can read about like the like uh, what each optimizer is kind of doing below the hood. Um, but a stochastic gradient descent is like the like SGD in particular with momentum is the most simple one, or well, one of the most simple one. And I think this is the update rule. As I mentioned, basically you have some like factor for the previous value from the previous iteration, and you add some value from the gradient with respect to the loss function, and it optimizes these parameters and based on your input and your outputs. Uh, and then based on this, you will update your wakes. So, and then you repeat that as many times as you need. And like if we think about it, like in particular, the one that we are using, it's called SGD with momentum. And then the idea is that they call it with momentum because it says that, okay, if the network keeps like moving in this direction, it has like this momentum kind of like second order kind of idea, so that basically it's kind of accelerating in this direction across different steps or something. And therefore it's going to begin moving like faster because in all of these iterations, it has been moving in this direction. Again, if you're interested on this, if you take a deep learning class, you'll probably cover this and other things like ADAM and RMS and other things. And these things they were proposed, I would think, many years ago. HGD with momentum, I don't think, well, I think these ones are from like, I don't know, like maybe 2 decades ago. Maybe, uh, when was SGD with momentum proposed? I know that some of these optimizers, they don't even have papers. They were just published on, I remember one that was published on like a tutorial. Well, it says that, yeah, the ideas have been there for a while. Anyway, doesn't matter. We use that SGD with momentum to optimize like our parameters, as mentioned. What we want is move the parameters of the neural network to a local optimum. And if you ever have an opportunity to take an optimization class, traditional optimization class, I would say that's very useful. I took one. At that point in time, I didn't appreciate it, but looking back, it can be very useful. Yeah, and then, okay, so far we have covered the data preprocessing over here. So we have like data preprocessing component, like data loaders, all of that, very important, data visualization, then the neural network itself, then the loss function and the optimizer. Now to like put everything together, to wrap everything together, we arrive at the core of like the training of a neural network, the training loop. So usually we would decide like for how many iterations do we want to do this. Another way to do it is instead of deciding number of iterations, we decide the number of epochs. And in this case, an epoch is like running through over like all of the images in the dataset. If an epoch is going through over all of the items in the dataset, that's what like we call an epoch. So in this case, Cypher 10 has 50,000 images, and each batch size is 4. So if we divided 50,000 divided by 4, we'll get 12,500, if I'm right. So we'll have, this is the number of iterations per epoch. So each of our epochs is going to have 12,500 iterations. Of course, this is going to be a factor uh, of like the batch size, like how many iterations do we have. But the fact is that, okay, we have 15,000 images per epoch. Now there's two ways of like, as again, I mentioned there's two ways. One of them is we can decide the number of epochs. That way, the number of like images that we will see is like a certain, it's going to be epochs time number of images in training data set. The other way is like we can decide the number of steps. So each step has batch size, number of images. So in this case, batch size is 4. And let's say we decide on, I don't know, 1,000 steps. So in this case, we will have 4 times 4,000 for 1,000. That's 4,000. And then you would ask me why do we do it this way? Because sometimes actually what you care about is keeping the amount of computation that you do as a constant. So in this case, let's say that we are working with a bigger data set. So this is like 50K images, but let's say we are working with a smaller data set that only has another data set that only has 10,000 images. But we want to keep the amount of images that the network sees as a constant. Therefore, in this case, if we use, in the original case, in this case, we only use like, let's say 2 epochs with Cypher. With Cypher, 2 epochs would lead us to 100,000 images the network has seen. But in the other case, if we do 2 epochs, we would only have, the network has seen only 2,000, 20,000 images. So in those cases, sometimes we care about, okay, making sure that our network sees the same amount of images. So in that case, another way to do it instead of using epochs would be saying like, okay, we have a 4 batch size and we want to have like a number of iterations, n iterations, so that the network sees the same amount of images, which is 100,000. So in this case, the number of iterations would be 100,000 divided by 4, and that's 25,000 iterations. And therefore, in this case, now the number of images the network has seen is constant. Again, this is something that you can decide, and most like deep learning frameworks, they support training either using number of iterations or number of epochs. For now, let's just focus on number of epochs because this is the tutorial that they use. So they train over 2 epochs, and this is like the average loss across the epoch. And now the way that we access that data loader that I was mentioning earlier is like kind of like a syntax like this. Actually, it can be even more simple. We can do something like for data in train loader, and that's it. The way that they do it this way is because they are using this enumerate function, which also returns uh, another like variable, returning basically like a counter, like an I counter that goes from like 0 to the number of items in the dataset. I goes from 0 to the number of items in iterable. In this case, the number of items in the iterable, because we have 15,000 images and we have 4 batch size, the number of items in the iterable in this case is 12,500. So this will go from 0 to 12,500. And why we use this? In this case, they use it because they want to use this iterable, like each X iterations, they would like be printing the results. So yeah, that's yeah, like the reason why they do it, like using this like I data like kind of syntax. Again, yeah, that's one, like there's different ways to do the same thing. Then once we have that, like this data is actually returns the output of this Torch Vision datasets like class. When we call like a get item like method that that class has, and we'll go over that method later because actually you can return any item as we see right now. For example, if let's say you're working with text, you can return like text. It doesn't need to be like these labels that are like a categorical value. These labels, remember, that are something like 0 or 1 or 2 or something. Like actually in this case, it's 0 to number of classes. Yeah, labels, it's 0 to number of classes. And the inputs, as I mentioned, they have a size of B, C, H, W, where batch size, number of channels, like height and width. And the labels have also like batch size. Yeah, only batch size. Yeah, that's it. So labels can be any value from 0 to number of classes, but they have like batch size like of these values. Um, and then after that, so originally it comes in this tuple format. So we want to like, okay, unpack the tuple into like, okay, our variables that we can like then, these are like Pytorch tensors. Like both of these are Pytorch tensors. Uh, all of that is handled in that uh, like data loader and dataset class. The dataset class handles the conversion into the Pytorch tensor, and the data loader class, what it does, it takes it from being originally it was a Pytorch tensor of size CHW, what the data loader class uh, is train loader. What it does is it takes the original input that is something like this chw, and it would like combine the items from different processes, like so that we have now a batch size, like all of these items into a batch. So that's what the train loader actually does under the hood. Basically simplifies this process of making the batches from each individual image and each individual label, so that it's in a format that Pytorch can like uh, yeah, process. Then, because I mentioned we will maybe use a GPU, so we will move our data and our yeah, like basically our like inputs and labels uh, to the GPU, or if they are in the CPU, they would stay on the CPU. Then this one, actually I don't write it this way. Usually I write this optimizer zero gradient after the like optimizing step, but different people write this thing different ways. And I think it's because maybe in the past, originally the way that they designed PyTorch was this way. I think right now the common standard is to actually do it after doing the optimizer step. But for now, let's just say that, okay, this is related to the optimization. So you want to make sure that before you do the computation of your neural network, you want to make sure that, okay, there's nothing in the optimizer, nothing like left over from maybe some operation that you forgot or something. Then this is where we do like the forward loop of the network. Like this, we call the, like use this forward method of the network that is here. When you call the network directly, like an instantiation of the network, um, and you like give it an input, in this case it will like give it it will directly call the forward function, and that's one of the things that this NN module thing is inheriting from, this kind of style of call. Of course you can also like call it net dot forward, and this is doing the same thing under the hood. But yeah, this is the common way that we do it. And then therefore like we obtain like the processed like the predictions for our network. Now we compute the loss, as I mentioned earlier, something basically like, okay, we predict like a series of probability, like a vector of probabilities, and we'll be using this probability vector to compute the uh, loss function, like how far it is from the actual prediction from the ground truth. And then, as I mentioned, Pytorch, what it does, it simplifies this process of computing uh, like derivatives and like doing this optimization manually. So this is where it does the computation of the derivative, computes gradients in a backpropagation manner. So it's computing like this is the backward pass, and this one is the forward pass. This is like the loss function. Well, technically, this is part of the forward pass. So basically, if we imagine it as a kind of like, let's say, like something like a sequence of blocks, we have let's see, something like thicker. Yeah, maybe like that. Yeah. So if we imagine like the neural network as a sequence of blocks, and let's say we have an input x, and we input this input x into this convolution, and then we do the same after like a fully connected layer, and then we get like some vector of predictions we call y hat, and we have some like y, and this is like a loss function that actually computes the loss between like the actual prediction and the original one. Now we know, okay, what's the difference? What's the gradient? This is the symbol for gradient, like a delta triangle between like this prediction and this one. Then we can compute the gradient also for this one with respect to this one. And then finally the gradient with respect to this one. The way what we do that in practice is basically compute the gradient for this one, then multiply it by the gradient by this one, and then do it by that. Again, if you're interested in that, take a deep learning class or take like an online course or something. But that's kind of like the general idea of what it's doing. So this backward function, it's just computing these like gradients first, and then that's what the backward function does. And then what the optimizer step does is it's doing this step that I mentioned here earlier. Basically, I show you like an equation that shows the gradient descent like equation, something like this. You get the parameters for the next step based on the parameters from the previous step with some coefficients, like basically to like uh, decide, okay, like how much do we care about the previous step and how much do we care about the current step, like the gradients from the current step. That's the biggest difference between different optimization methods. And that's what the um, optimizer.step is doing, updating the parameters with respect to the previous time step and the gradients. Then again, as I mentioned, after this, usually I would like do the zero grade. This is the way I think it's like the common way to do it right now. But I think as long as you like do it either before or after, it should lead to similar results. Finally, as I again, we have been doing some computation here with some laws, and we want to make sure that whatever thing we are doing, it's working, and we know that it works because we look at some like we want to see something like this, that basically our network, as we train for longer, like the loss, it's going originally from a very high value. When it's making very wrong predictions, it's gradually learning new predictions over time to a certain point. And that's the kind of the training loop of a neural network. And again, after that, then these things are like kind of yeah, some other like functionalities, like you want to save your model to use it later, and you may also want to do the same thing. We originally did it with the train loader. We want to do it now with the test loader, but for the test loader, a few differences. The test loader, the first difference is that we do not care about, we are not training, so we do not need to calculate the gradients for our outputs. So we use this with Torch no grad, and everything inside of this uh, like wrapper. Now it's going to like not compute the gradients, and therefore it's going to be like much more computationally cheap. Uh, oh yeah, so it's going to be much more computationally cheap since we are not like computing the gradients for each of these steps in the neural network. Then aside from that, this is the same as previously. You basically take your data from your iterator, you move it to the GPU, you pass your out images through the network, and you will get some prediction. The difference is that in this case, what we care about less is the loss function. Of course, you may also care about the loss function, so you can also compute the loss function. But in this case, they focus more on the actual prediction. We care that the network, the predictions are correct. And again, as I mentioned earlier, the predictions that we make are not like discrete value. They are not like 1 or 2 or 3. What the network outputs is actually something like this, like a vector of probabilities. But the thing is that this vector of probabilities, we can actually select the one with the highest probability. In this case, it will be like the third one using this math function. And therefore, like we can select that one as our prediction. So now we assume that that one, the last one, is like the prediction. Let's say that this is a three class classification problem. The first one maybe like air, like plane. The second one is like car, and the second one is like dog. So our model is predicting dog, and that's the label that we use. And the way that we implement that is something like this. And then what it does is basically, yeah, basically we are adding, since we want to compute the accuracy is defined as the total amount of image, like the total amount of correct images divided by the total amount of images. So we add all of the images in each iteration to a total here. And then we add the amount of correct images by basically comparing these predictions against the labels. So if this prediction, let's say it's the prediction in this case will be from a vector, let's say, because this starts from 0, so in this case the prediction will be 2, because this is like 0, 1, and 2. And let's say the actual ground truth was 0, or let's say it was 2 or any value. So let's say it was 0. So because this is not equal to 0 is not equal to 2, therefore when we compute this predicted equal to labels, it's going to like give false, and therefore this is going to be like a 0. But let's say it was 2, it's going to like say 2 equal to 2, so this is like becomes true, and then it will like add it up, so it will become a 1. And therefore it will be doing this for all of the, because this is are both like tensors, so it will be doing this for all of the images in the batch, all of the predictions in the batch. And therefore, let's say in a single batch, we may predict like, okay, let's say the ground truth was 2 and 0. And in our case, we may have like two tensors, like one of them is 0.5, 0.3, and 0.2. In this case, our predictions would be like, let's say both of them are 0. So in this case, the first one will be wrong, and then the second one will be right. So we would have like an accuracy of like 50% in this particular batch. So the number of correct will be equal to 1. But because we only have like 2, then it will be like, yeah, like 1 divided by 2, and therefore like that's our accuracy. Yeah. So